I put this up partly to entertain you as you were waiting for the class to start, but also partly to remind myself to talk to you. I just want to make sure that you're all doing something to make sure that you have access to computational resources that you need. Be that the lab notebooks, or your own machines, or supercomputer, or Google Compute Engine, whatever it is. Just remember to have access to something that will help you compute things fast, okay?
If we're using like a co-lab GPU, how long, like for the labs that are in this class, like not including the final lab, how long would be the longest we'd have to wait for it to train, do you think?
I don't know. So we're trying hard to account for that in our labs so that you don't have to spend 2 days training.
Okay.
Yeah. So we will, if at any point we give you a lab where we expect that computational side of things will be significantly worse than what you're used to, we'll let you know. Good. Okay, so let's dive in. So today I wanted to talk, or last time we talked about convolutions and the receptive field of neurons. We talked about the power of small convolutions. And so today I wanted to talk about one last bit of sort of neural nets as we set them up, which is initialization. And I realized, as I was getting my slides together for this, I realized that we never really talked about batches. And we never really talked about stochastic gradient descent. Is that right?
Yeah.
Okay, so when I say stochastic gradient descent, who knows what that means? Okay, like almost none of you. Great. And when I say batch, like a batch of data, who knows what that means? More of you, okay, or you can guess, right? And mini batch, sort of guess. Okay, stochastic gradient descent. Okay, I'd like to very briefly then, I don't have slides for this, so we're just going to wing it on the whiteboard. And I hope this goes well. We'll see. Give me just a second, we'll boot up the lights. Yes. Oh, no. Okay, what I'd like to do is just very, very briefly talk to you about stochastic gradient descent versus gradient descent. And this will hopefully motivate batches. And the reason we care about batches is because we're going to talk about initialization. Okay, so we are talking about parametric function approximation. This is like the core of what we consider learning. So we have some model, which we'll call f, and it's parameterized by some parameters, theta, and it accepts as input some, say, image, and it spits out as output, say, some label. Okay. And I'll just say xi and yi. And we are given a data set, typically when we're training, and it's a set of xi, yi pairs, where I is 1 to k, where k is the total number of training examples that we have. Okay, and then we talked about loss functions. And we said, well, there's some loss function that we define on L sub I, so on each individual training instance. And we'll say there's some loss between what our function approximator predicts on xi and the true label yi. With you so far? And you could also call this so this is our prediction, and this is y, sometimes it's called yi hat, where hat means approximate. So there's an approximate yi, there's the true yi, the loss function on a particular instance tells us how happy or unhappy we are with that prediction. So notice that yi depends on theta. Therefore, loss sub I depends on theta. So as we tweak the parameters in our function approximator, this loss changes. Okay, and then over the course of the entire data set, we can define some L, and maybe it's I equals 1 to k, L sub I. And so the loss will depend on theta. L sub I is a function of xi, yi, and theta. Okay, good so far? Okay, any questions so far? So when we say gradient descent, what we mean is the following. We say, well, okay, so we're going to start off by guessing at our parameters theta. And gradient descent is the process where we take the gradient of this loss function, with respect to the parameters, and we take a step, calculate the gradient, take a step, calculate the gradient, etc. So we would write that as gradient with respect to theta of L, which is a function of theta. And so implicitly, this is also dependent on all of our x's and all of our y's, but I'm not going to write that. Okay, so take the gradient with respect to theta of L sub theta. Now, gradient is a linear operator. Linear operator? Who knows? Like, we good with that? Or do we need a quick review? Okay, so a linear operator has the following, so linear functions in general have the following forms. F of x plus y equal to f of x plus f of y. This is the definition of a linear function. A linear operator is something, an operator operates on a function. So a linear function, a linear operator takes a function and does something to it, but that something is linear. So if, for example, we took the gradient with respect to theta of some f of theta plus some g of theta, then because gradient is a linear operator, that is equal to gradient theta f theta plus gradient theta g theta. It's like the little gradient operator distributes. By the way, other operations that you know and love are also linear. So for example, the expectation operator in statistics is linear, and the integral operator is linear. Okay? Okay, so gradient theta loss theta. So this is linear. And so that means that if we push this over here, over I, we can pull this constant out. That's just a constant. So that's 1 over k, gradient, sum of the LI's. But we can also, so this is like the loss on the first one plus the loss on the second one plus the loss on the third one. So we can actually push this inside the summation. So we get 1 over k, the sum over I, gradient theta, Li, which depends on xi, yi, and theta. Okay, so what does this tell us? This says the gradient with respect to the parameters of our neural net on the loss function, the true loss as defined over the entire data set, is equal to the average of the losses computed on, of the gradient of the losses on individual data points. In other words, I can take an individual data point, so it's input and it's output. I can calculate the gradient of the loss. That's going to give me some vector-y thing. And then I can just take all those vector things and add them up. And this will give me what is called the true gradient. Okay, so what is the complexity of calculating the true gradient? Big O, like what? Big O, Okay, be bold. Big O what? Big O K, Brian West. Right? Big OK?
Yeah.
Why is big OK?
Because we do things.
Okay, right. So we have K data points. Probably I should have used N. Okay, so big OK. I have K data points. I compute K gradients, and then I average them together. Okay. So, and then plus whatever the complexity of actually computing the gradient is, right? But this is going to scale linearly with the size of the data set. Okay. So a very early observation in machine learning, and in particular deep neural nets, is the following. This is the exact gradient. But actually, you can think of this as, so whenever you see an average of a bunch of things, you can often think, you know, this is actually like an expectation. And that expectation is being taken over the data set distribution. So an average, so it's almost like you can think of the true gradient as a sort of like this, it's the sum of a bunch of individual random variables, and there's some expected value. It's like I have all these little gradients, and I'm averaging them all together, and that's giving me the true gradient. So but a little bit of statistics ought to convince you that if I'm trying to calculate the mean of this quantity, so this is an average, and I know how to calculate it exactly, could I approximate it? Could I approximate it and have a pretty good estimate of this gradient with fewer than k things? And so you guys probably all remember like the central limit theorem, which says what? Yeah, like anytime you're trying to like calculate the expected value of something, it's like Gaussian distributed. And as you have like more and more things, like that Gaussian becomes more and more Gaussian and tighter. And how many things do you need to get a pretty good estimate of the mean of that Gaussian? Like 30. So if you have 60,000 data points, this is saying if you want the true gradient, you have to do 60,000 individual gradients. But if you're willing to tolerate a little bit of noise, and if you're okay with a pretty good statistical approximation, how many do you need? Like 30. Okay, so stochastic gradient descent says, let's not compute the exact gradient. Let's subsample the data randomly. And I'm going to sample like 30. Typical batch sizes are 30 to 64. I'm going to sample like 30 data points. I'm going to calculate the gradient on those 30 data points, and I'm going to pretend that's the true gradient. And I'm going to plug that into my optimizer, and away we go. Okay, so what is the complexity of stochastic gradient descent?
Constant.
30.
Bingo, 30. Yes. Right, and 30 is like way less than k, especially if you have really big data points, really big data sets. Okay, so you might think this feels like a lot of post hoc justification for like just cheating, which is sort of it, I think. But actually, it's really interesting. Stochastic gradient descent. So first of all, it's way faster. I mean, like unimaginably faster. Second of all, it has some interesting properties. So it turns out that, so let's suppose we have back up a little bit. Let's suppose our data set, we have 60,000 data points in our data set, and we decide we're going to subsample and we're going to only take 30 at a time. So so let's suppose it takes us 60,000 time units to take one step in the true gradient, with using a true gradient. If we take a batch size of 30, how many stochastic steps can we take in that same amount of time? 30 equals 2,000. So you can take 2,000 steps using stochastic gradient descent in the same amount of time it takes you to take one step using the full gradient. And it turns out that it's way more important to be able to take more steps than better steps. You'll get almost exactly the same place, and you'll get there orders of magnitude faster. And there's another benefit, which is that stochastic gradient descent is more robust to local minima and other problematic areas in your cost function. And the reason for that is because if you get to some like local minima, it's probably not really a local minima, and if I add some noise to the gradient, it's just like I'm just going to hop out of it. So it's like faster, it's more robust, and works just as well. Actually works better. Okay, so this is stochastic gradient descent. And this number right here, anybody want to guess what this is called?
Batch.
A batch. This is your batch size. Okay, so when we say 30, like run with batches of size 30, this is what you're doing. You're saying we're going to stochastically approximate the true gradient by just sampling 30 random points, calculated gradient on those, and away we go. Okay, questions?
Could you like formally define the stochastic gradient descent? Because so is it taking just like 30 points and doing the gradient?
Yeah. Okay. Yep. So we'll say here's the formal definition using notation. Hopefully this is what you want.
Is that where B is your batch? So 30 in that case.
Yeah, hold on, I'm going to change the notation here just a second. J sampled uniformly from data set. Okay, this is the formal statement.
So-
Stochastic gradient descent says the true gradient is approximately equal to this sum, where the indices that you're summing over are samples uniformly from your data set.
Uniformly isn't like you choose at like equal intervals or like.
No, meaning to pick my first, so if I have 60,000 data points, I pick one uniformly randomly,
Okay.
and I say that's my first one, and then I pick the next one uniformly randomly. I might even get the first one again, and like that's okay
Yeah, doesn't matter.
with a small, 1/60,000 probability.
Okay.
Okay? Yes.
So in most cases, when we try to find the loss, we want to try to get to zero, right? Like we don't want to have any.
Yep.
If you want to try to get to zero, why when we get stuck in like a local minima, why can't we just like see if we're in the neighborhood of zero and try to like do something to get out of it?
So it's true that if you could get to zero, then you would probably be done. This depends on your cost function, though, by the way. It's not totally true that your cost function will always even go to zero. Sometimes it does. But so really, when you're going, and you get to like some, I don't know, some region of the cost function, typically you're far away from zero. You don't know what you're supposed to do. Sorry, am I answering your question?
Well, so like, so a lot of times our learning would get stagnant because we get stuck in a local minima.
Well, sort of.
I mean, sometimes.
Sometimes, actually, that's very rare. It's usually a plateau.
Oh, okay. But if we know like where we want to get to at the end, why can we develop a method where we can try to get out of it, but like seeing if we're around where we want to be?
So there are, so I think the answer is you don't know how good you can do. So if you get to some plateau, it's true, like maybe, so let's suppose we knew that the global minimum was zero.
Right.
And you run your optimizer and it gets to like 10. And I think what you're saying is well, we know that 10 is not zero.
Right.
So let's do something to get better. The question is, what is that something? Like nobody knows.
Right.
And furthermore, you don't know if 10 is, you know that 10 is the best that your loss function could be, but you don't know that it's it may be that 10 is the best you can do with the neural net you've picked. In other words, it may be that your neural net is not cool enough, like it's not a good enough approximator to get you to zero. Like maybe 10 is the best you can do. If you picked a different neural net, maybe you could get to zero. Does that make sense? So there's no we just don't know how to magically hop to zero.
Right.
Okay, hopefully that answers your question. Okay, a couple more hands. Let's go.
Just a quick question. So say you trained your neural net for weeks or whatever, and say it's really big,
Yeah.
and you get to some plateau, or you just kind of leveled out in your gradient, like you're not getting any better. Is it fairly difficult to introduce random noise and start again to what your weight settled to?
There are many ways to deal with what you're talking about.
Yeah.
So random restarts is a thing where you randomly reinitialize all of your parameters and re-optimize, and then you can do an ensemble thing where you average a bunch of models together. There's cyclic learning rates where you can jack the learning rate up really high and you like bounce all over the place and then drop it really fast and you'll coalesce, and then you jack it up and drop it down and jack it up and drop it down and keep doing that. There's parameter averaging that you can do. So there's lots of tricks. We'll talk about several of them as we keep going. Okay, question back there. Go.
If I understood in lab 2, we were using stochastic gradient
Yes,
descent,
you've
but
already used it.
not with resampling, unless I misunderstood.
Actually, I think that's true, right? I think you just shuffle the data set and then randomly pick stuff out. Yeah, but that's fine too. Except all you have to do is just make sure that, I mean, the conditions here aren't super strong. Probably to be formal about it, you probably have to actually sample with replacement, but it doesn't matter for what we're doing. Totally good enough. Go ahead.
So if I understand correctly, the only reason why we do a batch size of say 30 or in our lab 42 instead of 1 is just so that it approximates the true gradient.
Yep. So you can take more steps, you can take them faster, it does a better job of escaping local minima, and you can fit it on the GPU RAM that you have.
But that's if you did the whole set, but if you did just 1, you don't want to do 1 because it might just take you in the wrong direction, the gradient.
Oh, a batch size of 1?
Yeah.
Batch size of 1 is totally fine. But then you just have a lot of noise in your gradients.
Okay.
Yeah. And so then you just have to make sure that your learning rate is correspondingly smaller. Okay, I thought I saw one more hand, and then we got to keep going here. Are we good? Go ahead.
So is an epoch every time you
Yes, so an epoch is every time you make one entire pass through the data.
and then you choose to step down the gradient, and then the next epoch is when you step again?
No.
No.
No. So you step after you calculate the gradients for each batch.
Right.
So I grab 30 data points, calculate the gradient, take a step. 30 gradient step, 30 gradient step. And when I've done that 2,000 times, that's one epoch.
Ah, okay.
Okay? Yeah.
So if you're always just randomly selecting data points, how do you know if you've actually passed through all the data points first?
Yeah. So either you do what we were just talking about, which is you don't actually randomly uniformly sample. You just take the indices of your data set and permute them. So that way they're randomly ordered, but you're guaranteed to get each one once. Or you just do it 2,000 times and you know that that's in expectation you would have hit all your data. Yes?
Okay, so the batch type, we're picking that many training points and then plugging what we get based on, okay, so we have our like network with our weights and we can plug training points into it and get a loss out. And so the batches, we're getting a certain number of points and plugging them in and getting the loss out, and then we take the gradient with respect to that, and that's not randomly sampled, that's just calculating the whole thing.
The loss is calculated
Yeah, so
deterministically
the
given
gradient,
the
yeah,
batch.
so the gradient is calculated deterministically.
Yes.
And then we step based on that gradient,
Yes.
and then just repeat for all.
Yes.
Okay.
Yes. You got it.
I think I was mixing up the picture in my head with like randomly sampling like weights
No.
to adjust.
Nope. Randomly sampling
And-
data points.
Yes.
Yes. Okay,
So
good.
that's different.
What's different?
That looks different.
Dropout? Yes, this is totally different. That's dropout, which we probably are not going to get to. But we'll try. Okay, great. So now that you know what a batch is, I think we are prepared to discuss what I wanted to, which is initialization. So, and this is going to be, the reason we talk about this is because this emphasizes some intuitions about kind of getting things to work and some strategies for understanding why it is that certain models work well and certain models don't work well. Okay, so I think we've already sort of answered this, but let's imagine that I have a very simple neural net. So let's suppose there's some nonlinear stuff in here, but I have some hidden layer, and I have these weight matrices connecting input to hidden and hidden to output. And let's suppose I initialize it all the weights to 0. So what happens? Good idea or bad idea? Bad idea. Why is it a bad idea?
Change uniformly.
Because everything looks indistinguishable, and so the gradients for every parameter is going to be the same. They're all going to update in lockstep, and nothing will be learned. Okay, so you say like, okay, clearly I can't use 0 as my initial condition. So your first idea is probably, well, let's use random numbers. And I don't know what random numbers to use, so let's use Gaussian numbers. And, I don't know, let's kind of make them small. So I'm going to initialize my weight matrix with some, so this is uniformly random numbers with some size, DYH. And I'm going to multiply by 0.01, that'll give me kind of a small standard deviation. And this is how I'm going to initialize all of my weights. This is my initial guess. Okay, this works okay for small networks, like 1 or 2 or 3 maybe layers, but leads to very strange properties when you start plugging it into deep networks. So here's what I mean. So I want to take you through just some empirical observations now about why this simple idea seems like pretty straightforward, what could possibly go wrong. Take you through some simple things. So here's the idea. So we're going to have a little 10-layer neural net, 500 layers per neuron, and there's a little bit of code here. We're not going to go through it. But the idea is that I'm going to go ahead and take this neural net. We're going to randomly initialize all the parameters. And then we're going to start by plugging some data in at the beginning. We're going to propagate that data through the network. And we're going to track each layer. And we're going to look at the distribution of activations of the hidden nodes. We're going to plot them. So I'll show you what I mean in just a second. So here's an example. So here's our 10 layers right here. And the little histogram shows you the distribution of what the hidden layer units look like over a data set. And here we're plotting the mean, and here we're plotting the standard deviation. So, so let's look at the very first thing right here. So what does that look like? So this is the distribution of activation statistics of the very first layer. So we've taken our data, we've passed it through the first matrix, which had small Gaussian numbers. And what does the distribution look like? Kind of like Gaussian, yeah. It's got, what's its mean? 0, what's its variance? I don't know, like this is 1 and -1, but you know, that's kind of like 0.01 or something. Variance, maybe 0.1, 0.2 standard deviation, right? A nice, tidy looking Gaussian. But then what happened on the next layer? So what's the mean? 0. But then much less variance. And then what happened on the third? It's essentially 0. So, okay, so this little neural net, we plugged normal Gaussian looking stuff in. Our weight matrices were just kind of randomly Gaussianly distributed. And after just a couple of layers, after propagating information forward, a couple of layers, all of a sudden, all of our h's are 0. What's going on? Yeah.
When you add lots of normally distributed variables, the variance is you add it to the square root. So that's
Okay.
why the layer standard deviation is equivalent to the square root of the fashion.
Yeah, so you can see, so the means are staying at 0, but the standard deviations are going down precipitously. Or another way to think about it, all right, so another idea?
I'm just confused. Is this after training or is this just
Right,
initial?
this is just the very first time. So we just plug some data, like we have to calculate our first gradient. So I'm just looking at the activation statistics of the forward pass through the network. We haven't even gotten to the backwards pass yet. Just the forward pass. We haven't even taken a gradient step. We're just going to try to compute the gradient. I just want to know, what does the forward pass look like? And I'm just noticing that all of my hidden layer activations are 0.
When you multiply little numbers by little numbers, you get really little numbers?
Yes! Right, so all of our W's are composed of numbers that are smaller than 0. I'm sorry, smaller than 1. It might be smaller than 0. If they're smaller than 1, that's going to be a little number. So I take a bunch of little numbers from the previous layer. I multiply it by a W, which has a bunch of little numbers. It gets littler. And then multiply by another W, it gets littler. And I keep going. It gets littler, 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 and eventually vanishes. Okay, so yeah, so all the activations are becoming 0. And what will the backwards pass then look like? Zeros. So the fact that, so we've talked a little bit before about how nonlinear activation functions like sigmoids can kill gradients. This is another way gradients can die. Gradients can die if numbers get too small. And if all of your weight matrices are just like randomly sampled Gaussian numbers, which are kind of smallish, things can vanish, especially with very deep networks. So, and this is just the forward pass. It says nothing about the backwards pass. Okay, so, okay, great, you say. Dr. Wingate, thank you so much for this inspiring lecture. You were absolutely right. This little bit of code right here, 0.01, clearly the wrong number. So instead of 0.01, I'm going to change my code, and I'm going to just use 1.0. Right? So let's just make the numbers bigger. Okay? So let's look at the first layer, hidden layer activations. So what happened?
Well, we have the opposite problem now.
You have the opposite problem. What happens?
Well, your numbers are too big, so they're all going to...
So everything's getting pushed out, and then I think there was a sigmoid in this network. So then what happens?
You get pushed further and further out.
But they're clipped at,
1.
or I think they have 10 inches, right? So they're clipped at 1 and -1. So everything gets pushed to 1 and -1. Then we take a bunch of things that are 1 and -1, we multiply it by a weight matrix, and that gives us stuff that's, I don't know, like 10 or -10, but that gets clipped to 1 to -1. And then, bam! Nothing but bad activations all the way down. Okay, so what do you do? So clearly,
Did we try a uniform distribution yet?
yeah. So uniform distribution doesn't matter. So okay. So the problem here is that if the numbers are too small, you get zeros. If the numbers are too big, things get pushed out too much. In either case, the gradients are 0. So you might say like, oh well, clearly I could just try like 0.02, 0.025 or something like that. So some people have thought about this problem, and there's this very famous paper by a fellow named Xavier, and he said, okay, here's what you want. If you ask what should the variance of your initial parameters be so that gradients don't die, either because they're too small or too big. He thought about it really hard and came up with this rule, which is you want the variance of the weights to be proportional to the number of things coming in. So basically, if you have a layer with a lot of things coming in, then you want things to be smaller because you're going to be adding them all up. If you have a few things coming in, you want it to be bigger. And if you use this rule to initialize your W's, what do you get? This is like gloriously beautiful Gaussians all the way down. This is called the Xavier initialization rule. Okay. And so you might think like, well, Dr. Wingate, you told us that we should never use tanages or sigmoids. So aren't you like feeding a little bit of a straw man here? Let's use ReLUs. So what happens if we take the Xavier initialization rule and plug it into ReLUs? Or sorry, change our network so that instead of tanages it has ReLUs. This is what you get. So talk to me. Okay, so what do you notice about the hidden layer activations here? Talk to me about this one right here. I hope you can read that. I'm sorry, this is kind of small. I would have like missed 10% on my IPython notebook for tidy and legible axes. Okay, so this is 0 here. So what's the first thing you notice about hidden layer activation statistics? They're all positive. Why are they positive? Because the ReLU, that's what the ReLU does, right? Things coming out of ReLUs can only have positive entries. And why do you have a huge spike at 0?
Because all the negative ones.
Yeah, everything that would have been negative got collapsed to 0. So you have a huge spike at 0. So the first layer doesn't look too bad, I guess. I mean, if we were to rescale this and just chop this spike off, you can sort of imagine that that would look kind of Gaussianish. Okay, but what happens over time as we get deeper, deeper, and deeper into the network?
The 0.
Yeah, everything starts going to 0 still. So so if ReLUs, if you use the Xavier initialization rule, after about 10 layers in a neural net, gradients will vanish, and you will be unable to train your model. And I think we don't have to go in detail. I think you can sort of imagine why this is happening. Like, oh yeah, like the ReLU means that only positive numbers are going to come out, and those positive numbers are going to get multiplied by a weight matrix. Some of them will have been zeros, so like a bunch of things will die, and then some things will be positive and negative, but then half of them will die, and then maybe half of them will die, and half of them will die, and half of them will die, and there's very few things that sort of make it through the gauntlet all the way to the end of the network. Okay, so there's this other very famous, I'll get you in just a second. There's this another very famous paper, that's a fellow named He. And he said, divide by 2. This is the only publication I know of where the entire paper, like this is the sum total of the paper. So you take the Xavier initialization, but there's kind of good reasons for this. No, I mean, like there's like some analysis and stuff. But the practical consequence is you divide by 2, and notice what happens. Right? You get a very nice distribution of activations, and they propagate cleanly through your entire network. So this is just saying the Xavier rule, when you're using ReLUs things get a little too big, the numbers are a little too big. And, or sorry, a little too small, right? We need them to be a little bigger, a little more spread out. And, okay, so, turns out that when you wrote your PyTorch code, and I think some of you, like this is a question that you're gonna be asked in, I think, lab 3. And so when you're building your first DNN, it's gonna ask you about initialization. And it's gonna ask you to do some random initialization and the Xavier or a key initialization. And so some of you might already know the answer to this, but when you create a variable in PyTorch and you want to specify, if you wanted to specify, hey PyTorch, initialize my variable and please use the Xavier/key initialization rule to sort of initialize all the initial conditions of that variable. How do you do that? Does anybody know?
Keyword argument?
What?
Uh,
Keyword argument? Is that what you're saying? Keyword argument?
Probably a keyword argument.
Probably a keyword argument. Yeah, so it turns out you do nothing if this is what you want PyTorch to do for you. The default behavior of PyTorch, when you declare a new variable and you want to initialize it, if you pass nothing, it will initialize it using this rule. And this is why. Okay, so you should just like know that. So that is like a free point on your lab somewhere. You can like just, I don't know.
Like it automatically uses the right one based on your function.
Well, no, it automatically uses this one. So it automatically uses the Xavier/key.
That would not fail in CanH.
Oh,
Like,
no.
do we have a picture where
No.
it plays nice with? Is it like it plays nice with ReLU but not CanH and
I don't know. I don't know if anyone's ever done that. Tested
Like,
that.
can you not just make that same picture?
Not in the PowerPoint.
No, not the PowerPoint. but like
Yes, in theory we could make the same picture. So my guess is, well, let's see if we can ask what'll happen. Let's see. So this distribution goes from 0, 0.51, 1.52, 2.53. So the question is, would it sort of stay centered between the tanh boundaries of -1 and 1?
This was a picture for he with ReLU.
Yes.
Wasn't that that?
Yep, this is he with ReLU.
And we like that.
So, yes.
Yes.
Yes, this is good.
There's no like okay.
Yep, yeah, so,
Multiple things
so
that-
why is this, so sorry, why does this look good? Maybe that's your question.
Yeah.
Why does this look good? So this looks good because this is saying plenty of things would have been negative, but they're getting killed because of the ReLU. The other things that are positive, they look sort of Gaussian.
Okay, so if we cut it off, it'd look like the other
It would
one.
look kind of like
We
Gaussian.
just have that big.
Yeah, the spike doesn't have
Alright.
the scale.
So
Sorry.
the spike makes it harder to see that
Yes.
there's a nice.
Yes.
Okay.
Just squint.
Okay, that makes more
Squint,
sense.
and this will look Gaussian.
So if you plot analog scale, it would look better. Or no, if you just cut off the zeros, you
Yeah.
can see that. Okay.
Okay, good. Go.
So when you say this is the default behavior of PyTorch, is what you're saying is that when you say sequential, and you say like linear, like convolutional 2D and so on, that if you don't put any weights into there, it just naturally makes this distribution.
Well, so when you do PyTorch, as you'll hopefully be learning this week as part of your lab, when you declare parameters for a particular layer, you have to give it some initial condition. And so there's like this function, and there are various keyword arguments you can pass to this function to initialize, declare how the variable should be initialized. And if you pass nothing, this is what it will do.
Okay, so my question is, we have these gradients that are consistently 0.
Yeah.
How do we know that there are some neurons that just aren't getting trained?
You don't.
So we could potentially be ignoring.
Yeah, so
a whole
it
set
is,
of neurons.
it is entirely possible that just because of the way you initialize things, there's a whole flock of neurons that'll just never get a signal and they'll never be updated, and that'll just be wasted RAM. Yes. Totally. Yes. But I think the odds of that are very small. But by the way, we know that neural nets are typically not minimal models. Like we know that we're over parameterizing this thing, and that's okay.
So, just one more about this. So it uses Xavier or he et al. Depending on whether or not you're.
No, I just always use he.
Okay.
Everybody uses he because they assume you're going to use ReLU.
Gotcha.
Yeah. But you should just be aware that if you're not using ReLUs, a different initialization rule might be appropriate. Yeah.
So with Xavier, we used, what did we use, TANH originally, and then we showed that with value of row. If you use this with like TANH and like sigmoid, does it still have a good distribution?
I think it actually does pretty well.
Okay.
And I think that's because picking the variance is based on what you want is you would like the hidden layer activation statistics to be roughly unit Gaussian. And so you just kind of do the math of if I have a weight matrix and I have a bunch of Gaussian random variables and I'm multiplying them together and adding things up, what's the variance of the result going to be? You just like kind of solve for that. And that's where this rule comes from. Hold on, we've got some more questions here. We'll start in the back and we'll work our way forward. Go ahead.
So if this was only discovered in 2015.
Yeah.
Weren't there a lot of successful neural nets before that? Cover the initialization stuff.
So it is possible, certainly it's possible to have, yes, so there were successful neural nets, but not a lot before this. It was like 2012 when the first really successful neural nets came out. And before that, yeah, like you just try stuff. I mean, seriously, like it was like even more of a black art than it is now. So now we at least have a little bit of an understanding of how to pick these things in a relatively automatic way. But yeah, before that, you just had to like fiddle with stuff. And it's not like, it's probably not the case that the gradients were actually zero. They're probably like really, really small and learning is really, really slow. So really good initialization helps because it'll just look faster. Okay, Eric.
That's exactly what I saw. I had an experiment where I did that, and it learned, like, those gradients aren't actually zero at this 10th layer. We were only doing like 70, so like, you're getting pretty close. But once you add that, it learns a ton faster.
Yeah.
Because you're using all of your layers.
Much more signal.
Rather than just your.
Yeah. Okay, right. Go ahead.
Is there a similar correspondence with orthogonal initialization? Is there a way that works for activation?
Yeah, so orthogonal initialization sometimes works better, sometimes works worse. The idea there is just to try to bias your parameters such that they'll learn different things, just like start them off the gate that way. Turns out that if you randomly sample like a matrix, like an n by n matrix with Gaussian numbers, and then you look at the correlation between all the vectors, they're basically orthogonal vectors. Not quite, but okay, one more question we got.
So, okay, the impression I'm getting is we use the he initialization because for TANH, Xavier is good and he is meh-ish. And for ReLU, he is good and Xavier is bad.
Right.
Okay, cool.
I think you got it. Okay, let's keep going. And there's tons of work on this. This is just some older papers you can check out. Let's see, yeah, okay, we've got 7 minutes, so I think we can move on to the next thing. So you might say, so I think I just sort of mentioned this idea that what we'd really like to do, just to make sure that our gradients can propagate cleanly all the way through our model, so we'll have a trainable model, is that we'd like the hidden layer unit activation statistics to be sort of Gaussian. Mean zero, roughly unit variance, like we don't want things to be too big, we don't want them to be too small. And so there's this idea called batch normalization. And the idea of batch normalization is, well, you want unit Gaussian activations? Let's just like make them unit Gaussian. And so the idea is we take some batch of activation, so we have a batch of data, we plug it into our model, and we consider some hidden layer. And we look at the distribution of activation statistics of that layer across the batch. And if we want to make it Gaussian, how do we make it Gaussian? Well, we just like take each activation for each of the k things in our batch, and we subtract off the mean of the things in the batch. That'll make it mean 0. And we divide by the standard deviation. That'll give it variance 1. And we'll call that our new activations. Okay? So notice that this is just another function. And is it differentiable? Yeah, I mean, we know how to compute an expectation over k things. We just sum them up and divide by k. And we know how to compute a divide, and we know how to compute a square root, and we know how to calculate the variance of a bunch of things. These are all just differentiable mathematical formulas. So the idea of taking an input set of hidden layer activations, transforming them with a little function that whitens them, and giving us some new activations, that's just another differentiable function. Now what's funny about this function though is that it operates across a batch of data. It's not operating within a data point. But maybe we can show it to you like this. So if we have n data points and we have d dimensions, then for each dimension, we just calculate the mean and the variance of each of those dimensions in our data independently. So this is our first layer, for example. For each pixel, we would calculate the mean and the variance of the pixels across our batch, and we would just make them white. By the way, does everybody know what I mean when I say whiten data? Whiten just means unit Gaussian, so mean 0, standard deviation of 1. That's called white noise. Go ahead.
When we normalize it by column, isn't that gonna get screwed up when we normalize it by row?
So,
Like
so
we're
we're not.
trying to, like we're not trying to normalize it in all the directions at the same time?
No, we only normalize, yeah, sorry, this picture maybe isn't the best picture. So in the past, I've drawn pictures like this, where we have things like this, where we have depth by height by width. And what I'm saying is, but then we're adding a new dimension, which is the batch dimension.
Let's keep going.
Okay, so this is for one, this is like one input image.
Yeah, that's the output, yeah.
Okay, and we're gonna go like through some neural net and we're gonna get some output.
Oh, so normalize differently for each thing in the batch?
No,
No,
we're
wait, oh.
using, so you can imagine we have a batch of images. So there's 30 of these. So this is a 3-dimensional tensor.
What if you flatten it first, just to show what you're talking about?
Yeah, okay, that's a good idea. So we can take this, thank you, that's a great suggestion. We've talked about flattening images. So this was 32 by 32 by 3. We could flatten that into a 3072 by 1. And then we'd have this one, and this one, and this one. There would be 30 of those. And that's what I'm stacking up here.
Wait,
So n is 30.
so each column of that is one of the flattened tensor outputs for a single image in the batch? That's the columns?
No,
Or that's the
each
rows?
row,
That's the rows.
each row.
Okay, so you're stacking them up as the rows?
Yes.
Okay.
Sorry, so I'm taking this, and I'm transposing it.
Oh, so we're normalizing for each neuron. So we're normalizing over the batches for each neuron in, like for each weight neuron.
For each
Okay.
plot feature.
Yeah. Okay.
Each